every function that's differentiable is also continuous. Let's see why. So remember that a function is continuous. Let's say y equals f of x. It's continuous at a point a if it's true that the limit as x goes to a of f of x equals f of a. So say now that you have a function that's actually differentiable at the point x equals a, which means that this limit of the difference quotient, has to exist. So if this limit exists, why must it be true that the function's continuous? Why must it be true that this limit exists? Another way to write this, so if f of x is getting close to f of a, another way to write that is to say that limit as x goes to a of f of x minus f of a equals 0. So for our purposes, it's going to be sufficient for me to prove this to you. And how can I do this? So one of the things you're seeing that we do all the time is this idea of multiplying by the number 1 or adding the number 0. Here I'm going to multiply by the number 1 because this is exactly the numerator of the difference quotient. So if I start with, say, let's start with the equation f of x minus f of a, then this is going to be equal to x minus a times f of x minus f of a. Divided by x minus a. So that's going to be true as long as x is not equal to a, no problem. So let's take the limit of both sides if we can. And if I can show that the limit of the left-hand side is equal to 0, then I'm finished. So what's the limit of the right-hand side? Well, I've got two things multiplied by each other, right? I've got x minus a, and I've got this difference quotient. So my product limit law says that the limit of this product is going to be the product of the limits so long as each one exists. Well, because this function is differentiable, that limit does exist. So now when I go and take the limit of this, and let me continue the calculation up here. So now when I take the limit of this left-hand side, that's going to be the same thing as the limit of the right-hand side, that's limit of x minus a times limit of f of x minus f of a all over x minus a. But the limit as x goes to a of x minus a, that's just going to be 0. We can plug that in and get a minus a. That's going to be 0. And now I'm multiplying that by, oops, I'm not doing anything if I drop my pen. I'm multiplying this now by f prime of a. So which is just going to give me 0, which is exactly what I wanted. So the very fact that the derivative existed tells me that this limit of the numerator has to be 0, which is the same thing as saying that the function has to be continuous.